Let me help you ace your pre-calculus exam by reviewing Unit 2 content on functions, domain, range, graphs, transformations, extreme values, compositions, and inverse functions. In problem number 1, we have various parts where the directions say to evaluate and simplify when the function f of x is defined by this quadratic expression involving x squared. F is the function name, x is the letter representing the input for the function, the independent variable, and this expression for any value of x gives you the output of the function, x squared plus 5x minus 4. We need to take the expression x, square it, then add 5 times that quantity, and then subtract 4. We could call this value y, but we don't have to. In part A, we do this when x takes on a numerical value. X is 3. We evaluate f of 3. We need to compute 3 squared plus 5 times 3 minus 4. Remember order of operations. You need to do the squaring and multiplying first before you do the adding and subtracting. 3 squared is 9. 5 times 3 is 15. I compute that first. I do not do 9 plus 5. I do 9 plus 5 times 3, 15. And then subtract 4. 9 plus 15 is 24. Minus 4 is 20. F of 3 is 20. If we were to graph this function when x equals 3, y would equal 20. In part B, we are evaluating the function at not a number, but an expression, 2x. This really is called a function composition. There's an inner function. We take a number x and multiply it by 2 first, and then an outer function, the function f itself, which is defined by this formula. This also corresponds to transformations of graphs, which we'll talk about later. So what we do, and this is confusing, but listen carefully, is we go up to this formula, and wherever we see an x, we replace that by the expression 2x. So when I see an x squared, I need to do 2x quantity squared. When I see a plus 5x, I need to do 5 times the quantity, 2x, then subtract 4. It's very careful. You need to be very careful in how you do this. 2x quantity squared means 2 squared times x squared. That's a property of exponents. 2 squared is 4, so I get 4x squared for what this simplifies to. 5 times 2x is 10x, and then we have a minus 4. In part B, the answer simplifies to 4x squared plus 10x minus 4. In part C, it gets even a little trickier. We are replacing the x up here, wherever we see it, with the entire expression negative x, or the opposite of x if you prefer. Be careful. So I need to take that x here and replace it with the negative x before squaring it, and then go to the 5x and replace the x with negative x, and then subtract 4. But of course, when you square negative x, you get the same as squaring x itself. You get x squared. This is the same as negative 1 squared times x squared. Negative 1 squared is positive 1, so it simplifies to just a plain x squared. But this, you're taking plus 5 times negative x. That's the same as minus 5x. So I do not get plus 5x there. I get minus 5x when you simplify, minus 4. Interesting thing to note is this expression, this quadratic, is different than the original function. We have gotten a new function here. This is not the same as the original function, and that ends up meaning this function is not an even function because f of negative x does not equal f of x. We'll talk more about that later. How about if the negative sign is outside the f, in front of it? Then you need to negate the entire output. You need to have the minus sign in front of the entire formula, giving you the output of f when you plug in x. So you get this. And when you have a negative in front of something like this, that's really the same as negative 1 times that expression. And by the distributive property, you can then and should distribute the minus 1 through the parentheses, multiply each term by minus 1, so you will get negative x squared minus 5x, and then negative 1 times negative 4 is plus 4. This is the answer, though you should realize when you look at this expression right here that that means negative x quantity squared. It's not the same thing that I did up here. Parentheses are very important. When you go on to part E, we are replacing the input with x minus 1. This gets even trickier. Go back up to the function formula. Everywhere you see an x, replace it with x minus 1. So I get x minus 1 quantity squared plus 5 times the entire expression x minus 1, then minus 4. Simplify. With the first expression right there, I need to realize I need to multiply x minus 1 times itself, so I will have to use the FOIL method to help me simplify that. First times first, outside times outside, inside times inside, and last times last. But with the second term here, I can just distribute the 5 through right away and get plus 5x minus 5. Don't forget to subtract 4. Continue simplifying. X times x is x squared. X times negative 1 is minus x. Negative 1 times x is another minus x. And negative 1 times negative 1 is plus 1. Plus 5x minus 5 minus 4 is the same as minus 9. Continue simplifying. X squared, what's the x term? It's negative x minus x plus 5x. That simplifies to plus 3x. And then the constant term is 1 minus 9. That's minus 8. So this function, f of x minus 1, which turns out to represent what's called a horizontal translation of the original function to the right by 1 unit, simplifies to this function. F is even more complicated. Take 2 times f of x minus 1 and then add 3. Actually, to save a little time, I can take my answer from part E, multiply that entire thing by 2, like this, and then add 3. I'd have to show these intermediate steps if I were doing this one from scratch, but we're going to go ahead and use that. Now distribute the 2 through the parentheses here, the distributive property, to get 2x squared plus 6x minus 16, then plus 3. That simplifies to 2x squared plus 6x minus 13. This corresponds to a horizontal translation to the right by 1 unit, a vertical stretching by a factor of 2, and then a vertical translation up by 3 units. We'll talk more about that later. Finally, in part G, we are simplifying kind of a strange looking expression. It's called the difference quotient. It's actually very important for calculus to be able to simplify things like this. Another weird thing about it is I have a different letter. Instead of an x, I have an h. Don't let that bother you. It could have been an x, but we're using an h now. Don't let it bother you. F of 2 plus h. I need to go back up to the formula for f, and wherever I see an x, replace it with 2 plus h. So I get 2 plus h, quantity squared, plus 5 times the entire expression, 2 plus h, minus 4, using my formula for f of x and replacing x with 2 plus h. Then I need to subtract f of 2. 2 squared plus 5 times 2 minus 4. Make sure you use parentheses. That entire expression is f of 2, and that entire expression is being subtracted, like I have there. All divided by h. Go ahead and expand this. 2 plus h quantity squared. I need to do FOIL just like I did up here. I'll do it in my head. First times first will be 2 times 2 is 4. Outside times outside and inside times inside are both 2h. Combine those, you get a plus 4h. And last times last will be h squared. Distribute the 5 through the parentheses there to get 10 plus 5h minus 4. Go ahead and simplify this expression. It's 4 plus 10 minus 4 is 10, and I'm subtracting that thing. I also could have distributed the minus sign through the parentheses here. All divided by h. Continue simplifying. The constant terms end up canceling. That will always happen with this expression when f is a fairly simple function like a quadratic. It turns out the constant terms in the numerator will always end up canceling. You can combine the 4h and 5h to get 9h, so we get h squared plus 9h, all divided by h. Can this be simplified further? Yes, it can. You can factor out an h out of the top to cancel it with the 1 on the bottom. Divide it out like that. H divided by h is 1, and 1 times anything is that anything. This simplifies to h plus 9. That is the final answer. Though it is good to realize that this is only true, this last equality is true as long as I'm not dividing by 0. This is only true when h is not 0. However, an interesting thing happens in calculus. What you end up doing is you think about what happens to these expressions as h approaches 0 but doesn't equal 0. These two things are the same when h is not 0, so they act in the same way. But this one is defined at h equals 0, whereas this one is not. At h equals 0, this one has a value of 0 plus 9, 9. That means this expression, and the original expression, in fact, gets closer and closer to 9, in fact, arbitrarily close to 9 as h gets sufficiently close to 0. and that has super important implications for calculus. In problem 2, we are given the entire graph of a function f, what you see right here in red, and we need to do various things. Evaluate the function at -2 and 2, find the domain, find the range, find intervals of increase and decrease, and ask the question and answer it, is f 1-to-1 y or y not? All right, so you need to understand how to interpret graphs first of all. F of -2. This is the output of the function when the input is -2. How is that done? You think of the x-axis as representing the input axis, and when x is -2, it means you're right there. To find the function value, you need to go up or down to the graph and look at the second coordinate. When x is -2, the corresponding point on the graph is right there, and the y-coordinate is -1. That means f of -2 equals -1. That's how to interpret this graph. How about f of +2? Again, go to the x-axis. That's the input. The y-axis is the output. You don't see a y here, it's not a big deal. Find f of 2. We go up to the graph in this case, and look at this point and its second coordinate. Its second coordinate is y equals 2. That means the output here is 2. F of -2 is -1. F of +2 is +2. Find the domain of f in part B. What does that represent? That represents the set, the collection of all possible inputs to the function. When you look at this graph, what are all the possible x coordinates? Think about the x-axis here and also realize that we are looking at the entire graph. We're pretending there's no more pieces to this graph. It doesn't go on forever to the right or to the left. What possible x coordinates are there? They go from the x coordinate of this point here, sort of ignore that little part right there, I think that's the assumption here, to this point. The x coordinates of those points range from -4 all the way up to +5. So that's the domain of f. You could write it in interval notation, the closed interval from -4 to +5, that's how you would write that. You could also write set Boolean notation, the set or collection of all x values that are real numbers. You could write x is an element of the real numbers if you like. This is not required. Such that, the vertical line means such that, or with the property that, x is between -4 and 5, including the possibility of equaling -4 and the possibility of equaling 5. You could write that as a compound inequality like this. So again, you read this as the set of all x in the real number system, if you like, such that, or with the property that x is between -4 and +5, less than or equal to's indicate that we have a closed interval here. For the range, we are looking at all possible outputs. What are all possible second coordinates of points on this graph? Well, the lowest possible second coordinate is down there, -4. What's the highest possible second coordinate? It would be the second coordinate of this point up right about there, which is bigger than 4. How much bigger? It's hard to say. Maybe about 4.2. Let's just go ahead and pretend that's the case. Your teacher would just expect you to estimate it here. So in interval notation, we would write the range, the set of all possible outputs, as the closed interval from -4 to +4.2, keeping in mind that this is an estimate, and again, that's all your teacher would expect. You could also write this with set builder notation, and for sake of clarity, to emphasize that it's a range, I'm going to go ahead and use the letter y to represent an arbitrary number in the range instead of an x, which was an arbitrary number in the domain. The set of all y in the real numbers with the property that y is between -4 and +4.2. Do I have to use a y? No, it's just for clarity to indicate I'm thinking about the y values along the vertical axis. What are the possible outputs here? Part D asks, on what intervals is f increasing and on what intervals is f decreasing? It is implied here when this kind of question that we're talking about x intervals, intervals in the domain. Looking at the graph, it's a little tricky. What values of x along the x-axis correspond to when the graph is rising as you move from left to right, going up? Like right here, it's going up as you move from left to right. And also over here. We have to estimate the x coordinates where we change from rising to falling. 1 point is right about there, corresponding to an x-coordinate of about negative 1.5. A point where we change from falling back to rising again is right about here, corresponding to x equals approximately negative 0.5, or maybe negative 0.4 or so. Let's go ahead and assume it's negative 0.4. So f is increasing when x is between negative 4 and negative 1.5, and also when x is bigger than, let's say, negative 0.4, up to the x-coordinate of this point, which is about, say, 3.6. We're just estimating it. I'll go ahead and use a union symbol to indicate that I'm saying it's increasing on both of these intervals. So I'd go from negative 0.4 up to positive 3.6, keeping in mind that these are estimates again. On what intervals is f decreasing? It's decreasing between here and here, between negative 1.5 and negative 0.4, and also when x is bigger than 3.6, from 3.6 to 5. So I could write the answers in interval notation as negative 1.5 to negative 0.4, and also I'll use the union symbol again, from positive 3.6 up to 5. Is it a problem that these boundary points, the negative 1.5 for example, and the negative 0.4 and the 3.6, go in both sets since I'm using closed interval notation? It's actually not a problem. Effectively, because at the boundary you are changing from one to the other. It's okay. The final question says, is f 1 to 1, why or why not? What does 1 to 1 mean? It means distinct inputs give you distinct outputs. Said another way, for any given output, there's only one input. That's kind of confusing. That definitely does not happen here, and the clearest way to see that is up here. There are distinct inputs, for example, say 3 and, well, slightly bigger than 4, 3 and slightly bigger than 4, that both give the same output, that both have the same second coordinate on the graph. This horizontal line crosses the graph more than once. That means this graph fails the so-called horizontal line test, and that means this function is not 1 to 1. What are the implications of that? It means the function does not have an inverse function. We'll talk more about that later. No, f is not 1 to 1. For example, looking at the graph that we looked at before, f of 3, and let's say looking at this number right here, it looks like about 4.2 or 4.3, let's just pretend it's 4.2, have the same function value. They are both equal to the second coordinate of these 2 points, which let's just say are equal to 3.8. So these two distinct inputs, 3 and 4.2, give the same output. That output, 3.8, has two distinct inputs that get mapped to it. That's enough to say it's not 1 to 1. Problem 3 has 3 parts and kind of complicated directions. Find the so-called natural domain and range, also known as image, of each function. Sketch the graph in each case. Identify maximum and minimum values and where they occur. And also identify any horizontal and or vertical asymptotes and where they occur. And we will use technology to help us here. So in part A, we've got a function f of x defined by this formula. Take the square root of the entire expression x plus 5 and then add 3. We are implicitly assuming real number outputs, though I'm saying that here. In a pre-calculus class, that would be the implicit assumption here. So we would say we're not allowed to take the square root of a negative number, and that helps you identify the so-called natural domain. We don't have to restrict the domain in some kind of unnatural way, is what the word natural means here. So we require for the domain that the input for the square root here, the entire expression x plus 5, must be non-negative. It must be greater than or equal to 0. Subtracting 5 from both sides, that's equivalent to saying x is greater than or equal to negative 5. Therefore, the domain of f, written d of f, in interval notation would be the closed interval from negative 5 out to the right forever. X being greater than or equal to negative 5 means on a number line we are at negative 5 or to the right of it, greater numbers than negative 5, forever. Going out to infinity, I'll put an infinity symbol here and I'll put a parenthesis, not a closed bracket there. What does this mean? It does not mean infinity is a number, okay? In a calculus and pre-calculus class, you don't treat infinity as a number. It's just shorthand notation to mean go to the right forever and ever, never stop. That would be the domain. How about the range? Well, now you need to know some things, if you're going to do it without a calculator at least. You would need to know that the so-called parent function of this given function, f of x equals this, you could call g of x is just the square root function, and you can know from just memorization that its graph looks like this. Its domain is all x values greater than or equal to 0, and its range, the set of all outputs, is all y values greater than or equal to 0. It actually does not have a horizontal asymptote. It kind of looks like it might, but no matter what horizontal line you pick, the graph will eventually get above it. So the range, again, includes all numbers y greater than or equal to 0. This function is obtained by first replacing x with x plus 5, which shifts the graph to the left by 5 units, and then adding 3, which shifts the graph up by 3 units. And so the graph of the function we're after here, this function, is about like this. Now I'm not going to draw it there because it would get confusing, but it's going to look like this, and it's going to go up forever and ever. It's not going to have any horizontal asymptotes, and because the lowest possible output is 3, when x is negative 5, the output is 3, the range of this function is going to be all y values, including 3, up forever and ever. If you want to use set builder notation with a domain, you'd be more likely to use the letter x, and again we could write as an element of the real numbers to emphasize these are real numbers, though that would be the implicit assumption even if you did not write that, such that x is greater than or equal to negative 5. And with the range, you'd be more likely to use the letter y to emphasize these are outputs, the set of all y that are real numbers, such that y is greater than or equal to 3. And yeah, I will go ahead and draw the graph now in a different color. When x is negative 5, you are at the lowest possible value of 3, and the graph looks like this. You could call 3 a minimum value, though it doesn't occur in a usual kind of way. It's not the low point of a valley. It's the left endpoint of the domain, and that is the lowest possible output. You could call this a global min, and it occurs when x equals negative 5. There is no global max to this function, again because the graph goes up forever and ever and gets above any horizontal line. There's no horizontal asymptote here. So I haven't written down all the answers to these questions, but I've at least described them. Let's go on to part B. Part B, we've got a quadratic function. With a coefficient of x squared that is positive, the graph is going to be a parabola opening upward. The only question is, what is the low point? That will help us find both the range and graph it and that kind of thing. But certainly the domain is easy. The natural domain of f is all real numbers. You can plug in any real number here. It's a natural domain because that's a natural thing to do. An unnatural domain would be to restrict the domain in some way, maybe because you are thinking about some application. But you could write just R here as emphasizing the domain is the entire set of real numbers. You also could use interval notation and write minus infinity to infinity. Don't use square brackets, use parentheses here because we're not thinking of these things as numbers. We're just trying to emphasize every number on the number line is a possible input for this function. To do the other parts of this problem, to graph it, to find the range, maximum min values, asymptotes, it's useful to complete the square to rewrite this function in what's called vertex form. So what you do to complete the square, since the coefficient of x squared is 1, it's a little simpler. You take the coefficient of x, which is 8, divide it by 2 to get 4, square that number to get 16, and just put the 16 in there. But wait a minute, how can you just put a 16 in there? Well, you can compensate by also subtracting it. That might look like it's a silly thing to do, but it's actually very smart, because when you do it, this part turns out to always be a perfect square, and in this case it's x plus 4 quantity squared. 10 minus 16 is negative 6, and this tells you all the information that you need to know. This is called the vertex form of the quadratic. It tells you the low point in this case, because the coefficient of x squared is positive, occurs when x is negative 4. This quantity will be 0 squared, or 0 when x is negative 4. And the y-coordinate will then be 0 minus 6, negative 6. The lowest point on the graph, and I will start to draw the graph here now, will be when x is negative 4, y will be negative 6. It's an upward pointing parabola. I could plot some other points to try to figure out where the x-intercepts are. Maybe I should, just to try to be a little bit more accurate. I could use I could try to factor it, or I could use the quadratic formula here to try to estimate where the x-intercepts are. So you get -8 plus or minus the square root of 64, 8 squared, minus 4 times 1 times 10 is minus 40 over 2 times 1. -4 plus or minus, that's a 24. 24 is 4 times 6. That'll be 2 times the square root of 6 because the square root of 4 is 2. -4 plus or minus square root of 6 will be where the x-intercepts are. Square root of 6 is between 2 and 3. -4 plus a number between 2 and 3 will be between -1 and -2. So the x-intercept somewhere there. The y-intercept of the function is 10. So we could mark a 10 here if we're trying to be accurate, be up there a little bit more. So the graph looks something about like this. We're not asked for x-intercepts, but I found them anyway. The range is all y-coordinates of -6 or greater. The range of f would be -6 to infinity, set of all y values in the real number system, y greater than or equal to -6. The -6 is the min value, and it occurs at x equals -4. There is no max value. The graph goes up forever and ever. And there are no asymptotes that this graph approaches, either a vertical asymptote where it's undefined or a horizontal asymptote that it approaches as x goes to plus or minus infinity. Part C, f of x is what's called a rational function, 2x plus 1 over x minus 1. Graphs of rational functions often have vertical and horizontal asymptotes, and this one's no exception. Let's first think about the domain, however. The domain of f would be all possible numbers you could plug in here where you are not dividing by 0. The only place we're dividing by 0 is when x is 1. So it's all real numbers x, I'll use set builder notation to begin with the property that x is not equal to 1. Did I say -1 before? I meant +1. So that is also written in interval notation as the interval from -infinity to 1, not including 1, unioned with the interval from 1 to infinity, not including 1. That would be the domain. Let's start to graph it. You can think about x-intercepts first of all. That's where this function equals 0, and it's only going to be 0 when the numerator is 0. 2x plus 1 equals 0. That will give 2x equals -1. So x is -1/2 will be the unique x-intercept. The y-intercept is the function value at 0. F of 0 is, plug in 0, you get 1 over -1, -1. That's the y-intercept. Asymptotes, vertical asymptote will occur where the function is undefined at x equals 1, though in general you do have to be careful. You don't necessarily, with rational functions like this that are ratios of polynomials, have vertical asymptotes every place where the denominator, the bottom, is 0. If the numerator is 0 at the same spot, you actually won't have a vertical asymptote there. So you have to do some factoring and canceling first in general. But these things are not 0 at the same place. So your one vertical asymptote is indeed at x equals 1. For your horizontal asymptote, well, they don't always have horizontal asymptotes. They only will if the degree of the top and the bottom are related in a certain way. You'll have a horizontal asymptote if the degree of the top is less than or equal to the degree of the bottom. Both degrees are 1 here. That's the highest power of x. 1 is less than or equal to 1. You do have a horizontal asymptote here, and in fact, when they're equal, it will occur at the ratio of the coefficients of the highest power of x. Y equals 2 over 1 in this case, which is 2. That's the ratio of these things. I'm not proving that. I'm just assuming that you've learned it. It can be reasoned out by thinking about what happens to this expression as x gets large, either positively or negatively. Essentially, the +1 and the -1 don't matter much. And essentially, it's like you got 2x over x, which is 2. That's what y approaches as x goes to either plus or minus infinity. And with simple rational functions like this, you don't cross your horizontal asymptote, though in general, you sometimes can. So what does the graph look like? We've got vertical asymptote at x equals 1, right there. Horizontal asymptote at y equals 2, say up here. That's y equals 2. You got an x-intercept at negative 1/2, a y-intercept at negative 1. And if you think about what happens as x approaches positive 1 through values just barely less than positive 1, like 0.9, 2 times 0.9 plus 1 is positive, 0.9 minus 1 is negative, and close to 0. You get positive numbers divided by very small negative numbers, making this fraction a very large negative number. You are going off to minus infinity there, which makes sense. It's consistent with these points. As you let x approach minus infinity, the output of the function will approach 2. You can double check that. And it does turn out the graph over here is kind of the flip of that. You can double check that by plotting points, and you get this kind of behavior right there. So domain is this. Got the intercepts, got the vertical and horizontal asymptotes. We have not technically identified the range yet, but we can do that now. The range of f is all y values in the real number system, except where this horizontal asymptote, y is not equal to 2. In interval notation, we'd write minus infinity to 2, union with 2 to infinity, not including the endpoints. Number 4 is about function composition. What fun. Let f of x be x squared plus 2x minus 3, a quadratic function, and g of x be negative 3x plus 2, a linear function. The directions say find and simplify each of the following. There's going to be 5 parts here. Part A, fog. Huh? Fog? No, that's not an O. It's a circle. F circle G, sometimes said F compose G. Yes, sometimes people do just say fog for fun. What in the world is that? Maybe your book actually doesn't use that notation. Maybe your book only uses this notation, f of g of x. You are plugging one function into another. We talked about this briefly in problem 1. G of x is the inside function. It gets done first. Then you take the output of that function and plug it into f. You work from right to left, from inside to outside. That's what we want to do here, and that's what this notation means. F compose g of x, by definition, there's nothing magical here, is f of g of x. Replace g of x with its output. That's negative 3x plus 2. And remember what we talked about in problem 1. No matter what expression is inside the parentheses, go ahead into the formula for f and replace each x that you see with that entire expression. It seems crazy, but that is what you do. So I need to replace the x with negative 3x plus 2 right there. And that means I need to square that. Then add 2 times that expression and then subtract 3. What is this circle for? It's just to emphasize that we can think of this as what's called a binary operation, as a way of combining 2 functions, f and g, to get a new function. Though we are interested in simplifying it, I need to FOIL here. I'm going to do it in my head. Negative 3x times itself is positive 9x squared. That's first times first when I imagine 2 factors here. Outside times outside and inside times inside are both negative 6x. Combining that gives me negative 12x. And then 2 times 2 is 4. Then I distribute the 2 through here. This is minus 6x plus 4 minus 3. Simplify. 9x squared minus 12x minus 6x is minus 18x. 4 plus 4 minus 3 is plus 5. There is f circle g of x, f compose g of x, or f of g of x if you prefer. This is actually a very important thing in both applications and in calculus in general. When you've got certain function compositions, it's actually more useful to decompose sometimes, to use something called the chain rule. It comes up in calculus a lot. Part B says find f of g of 1, which could also be written as f circle g of 1. I also could have asked the question that way. And you can do all this again. You could also just plug it into the simplified formula. Let's just check that you get the same thing. 9 times 1 squared minus 18 times 1 plus 5 is 9 minus 18 plus 5. That'll be negative 9 plus 5 is negative 4. That should be the answer. And if I do it step by step, if I first evaluate g of 1 and then evaluate f of that number, I should get the same thing. G of 1, plug in 1 here, is negative 3 plus 2 is negative 1. And then what is f of negative 1? Go up here, replace x with negative 1. Negative 1 squared plus 2 times negative 1 minus 3 becomes 1 minus 2 minus 3. 1 minus 5, which is negative 4. We do get the same answer, though you see it happens in a different way. This using the simplified formula up here, this doing it step by step. It's good to see that you get the same thing. Part C says find GOF, G circle F, or G compose F. G circle F of x. You might think, okay, I'm going to get the same answer as part A, I guess, right? Well, let's just see what happens. That's by definition G of F of x. Replace F with its formula, which is x squared plus 2x minus 3. And yeah, that entire expression gets plugged into G right there in place of the x. So we get negative 3 times the entire expression that gets plugged in place of x, and then add 2. Yep, that's the formula for G, negative 3x plus 2. Negative 3 times that expression plus 2. Order of operations, you've got to think about that in doing what you're doing here. Distribute the negative 3 through the parentheses, get negative 3x squared minus 6x plus 9, then plus 2, and simplify negative 3x squared minus 6x plus 11. Wait a minute. That's a different answer than part A. That's not necessarily going to happen, that they're going to be equal. You can get a different answer. In general, in fact, you do. Function composition, the circle operation in general is not commutative. F circle G and G circle F, fog and GOF, are not in general the same function. Once in a while they are, and there's one important circumstance where they are, but in general they're not the same function. What about evaluating when x is 1? I can plug into the simplified formula if I like and get this. And that will simplify to negative 3 minus 6 plus 11 is negative 9 plus 11 is positive 2. If I do it step by step, I should get the same thing. F of 1, go back up to the original f function here, plug in 1. I'll get 1 squared plus 2 times 1 minus 3 is 1 plus 2 minus 3 is 0. And what is g of 0? Plug 0 into there, get 0 plus 2 is 2. We do get the exact same answer as we had to here, okay? You wanted to make sure you can double check that. And we do get a different number than we got for part B. It's actually possible that A and C could be different answers, but B and D could be the same answer. It didn't happen here. It's not likely to happen. But in general, it could happen. So that's something to watch out for. Just because functions are not equal to each other doesn't mean that they don't sometimes give the same output. Oh, part E, G circle G circle G. I'm composing G with itself with 3 factors of G, you might say. This is G of G of G of X. Am I multiplying G of X times itself with 3 factors? No. If I did such a thing, I would get a cubic. But this is actually going to turn out to still be a linear function, we will see. Work from inside out. G of X is negative 3x plus 2. Then plug that expression into G itself. You can compose a function with itself. So I need to do negative 3 times that expression and then add 2. Before I do a final step, I should probably simplify this. Negative 3 times negative 3x is 9x. Negative 3 times 2 is minus 6, and then a plus 2, and then this simplifies to g of 9x minus 4. That expression now needs to get plugged into g, so I do negative 3 times 9x minus 4 plus 2 and simplify. Negative 18x plus 12 plus 2 is going to be plus 14. It is still a linear function. I made a bad mistake when I first did this and said negative 3 times 9x is negative 18x. No, it's negative 27x. So we get negative 27x, still plus 12 plus 2. Negative 27x plus 14, we get a linear function for the final answer. Amazing. Number 5 you can see is about a piecewise function. It's defined in pieces with 2 formulas based on 2 different conditions on the input x. F of x equals x squared minus 1 for the output if the input x is less than or equal to 1, and 1/2 x minus 1/2 for the output if the input x is strictly greater than 1. Part A. Evaluate first f of negative 2. Which case does negative 2 fit in? Negative 2 is indeed less than or equal to 1. It's to the left of 1 on a number line. Therefore, I use the first formula. I get -2 quantity squared minus 1. That's 4 minus 1, or 3. That will be f of -2. What about f of 1? 1 is at the boundary. Here x is less than or equal to 1. Here x is strictly greater than 1. Since 1 is indeed less than or equal to 1 and not greater than 1, it is still this case that we use. If we had switched and put the greater than or equal to here and a strict less than there, it would be the second case that we'd use. But we want to use this first case, so we evaluate 1 squared minus 1. That's 1 minus 1 is 0. That will be what we get for f of 1. Finally, f of 2. 2 is indeed fitting the second case. 2 is bigger than 1. So I do not square 2 and then subtract 1. Instead, I multiply it by a half and then subtract a half. 1/2 times 2 minus 1/2 is 1 minus 1/2 is 1/2. Part B. Evaluate a function composition, FOF, f circle f, f compose f of the input 3/2, which again by definition would be this, f of 3/2. All right, so let's just evaluate the inner quantity first, f of 3/2. 3/2 is 1.5. That fits case 2, so I need to use the second formula. So I get 1/2 times 3/2 minus 1/2. Simplify that. 1/2 times 3/2 is 3/4. 1/2 is the same as 2/4. So I'm ultimately evaluating f of 1/4. 1/4, however, is 0.25 is the first case. That is less than or equal to 1. So I need to use the first formula for that one. So I need to square 1/4 and subtract 1. That gives me 1/16 minus 1, which is 16 over 16. So I get -15/16 for the final answer. Part C, sketch the graph of f. You need to think about just these two cases. The function being x squared minus 1 in this case, and this 1/2 x minus 1/2 in this case. 1 is at the boundary. There's my x-axis, here's my y-axis. 1 is obviously going to be an important point. The quadratic x squared minus 1, okay, the graph of that is a parabola opening upward because the coefficient of x squared is positive. It doesn't have an x term, so the vertex is going to occur at x equals 0. The minimum value is going to be -1, and in fact that is the y-intercept here. When x equals 0, that'll be the low point. When x is 1, it does have an output of 0. We already saw that, in fact. So coming back down here and plotting a few points, like -1 here, you're going to get a graph about like this. And over here, it's got to be a mirror image of that piece of the graph. And it does continue looking like a parabola over here. And again, I could plot some more points to help me draw it better if I like. But over to the right of 1, it's going to look like a straight line with a slope of 1/2 and a y-intercept of -1/2. But be careful, don't actually draw the entire line. Draw just the part that starts here. And what is the limiting value of this function? Here we're talking intuitively about limits as x approaches 1 from the right. This expression, as x gets closer and closer to 1 from the right, like at 1.1, 1.01, is getting very close to a half minus a half, 0. And in fact, if you graph this line over all values of x, it would have an x-intercept of 1. It is a line that would go through this point with a slope of 1/2. Now, should I draw like an open circle there? No, I don't have to, because when x is 1, that's already covered by this case, and the output, in fact, is still 0, as we saw before. So in this case, I don't have to like draw some sort of open circle here. These two pieces of the graph do, in effect, come together at x equals 1. This is a continuous function. You can technically draw the graph without picking up your writing utensil. If you want a few more points, like for example when x is 3, because the slope of this is 1/2, the output of this would be 1 there. You could draw more points to try to draw more accurately, but this would be the graph. If you're interested, the domain of this is all real numbers, and the range of this would be all y values greater than or equal to -1. You can still talk about domain and range in such contexts. Number 6 is about inverse functions. Find the inverse function f inverse. This is not f to the -1 power. It's called f inverse. That's confusing, but it's standard. of each function f defined by the formulas below. Also state the domain and range of the inverse function. And also implicit in this is that we will need to discuss the idea of one-to-one again. It's one-to-one functions that have inverse functions. All right, so here we have a function f of x equals 3x minus 4. Domain is the natural domain, all real numbers. Its graph is a line with a slope of 3 and a y-intercept of negative 4. I will quickly sketch it here. It would look about like this, say. It is a one-to-one function. Every output has a unique input that gets mapped to it. Said differently, distinct inputs give you distinct outputs. It's such functions that pass the horizontal line test, no horizontal line goes through them more than once, that have inverse functions. This certainly passes the horizontal line test. It's got an inverse function. How do you find its formula? The standard technique is to say the function output equals y, to then take this equation and solve it algebraically for x in terms of y, and then at the end you switch the x and the y around. Now, truth be told, it's really only the first step of that that's absolutely necessary. I'll talk about y in a second here. But let's go ahead and do that first step. Solve for x. So I'm going to add 4 to both sides first and get y plus 4 equals 3x. I'm trying to isolate x. This can always be done with linear equations like this. Now divide both sides by 3. Y plus 4 over 3 equals x. And we are effectively done. This would be the inverse function, f inverse, if you let the input be called y. And that would be okay. Variable names are, technically speaking, not important. F inverse of y equals y plus 4 over 3, or f inverse of x, if I want to change the variable name to x, equals x plus 4 over 3 instead of y plus 4 over 3, represent the exact same function. Because it's you get the same outputs for any given input. The operations you're doing are the exact same. Take a number, add 4, then divide that number by 3. Take a number, add 4, then divide that number by 3. We are just more used to having x as the independent variable. That's one reason to do the swapping. Another reason is that when you do the swapping and call the output of this y and graph it in the xy plane, it's got a nice property that the graph of this inverse function is the reflection of the original graph across the line y equals x. So the graph of the inverse function would look about like this. I mean, you can rewrite this in slope-intercept form as 1/3 x plus 4/3. So the slope of that black line would be 1/3, and the y-intercept here would be 4/3. This would be 4/3 right there. The original function had a y-intercept at negative 4 down there, slope of 3, y-intercept negative 4. Here's slope of 1/3 and y-intercept of 4/3. That's a nice property, and that's partially why we justify doing this. But again, in terms of the answer, you could write the answer for the inverse function like this. You can also write it like that. Either way is okay. What about the domain and range? Well, the domain and range for the inverse function flip the domain and range for the original function. Now, I said the domain of the original function was the entire real number line. Its range is also the entire real number line. You can get, with this green graph there, every possible y coordinate, get every possible output. These get switched for the inverse function, but they're the same. They're both the entire real number system. So for the inverse function, f inverse, the domain and range are also both the entire real number system. But that's not going to be the case for all the problems, all the parts of this problem. And it's not going to be the case, in fact, for part B. Part B, f of x equals x squared plus 4, a quadratic opening upward. Think about it, its vertex is going to be when x is 0, you'll have y equals 4. That's not a one-to-one function if you think about the entire parabola. It does not pass the horizontal line test. There are horizontal lines that go through it more than once. F of 1 equals f of negative 1, for example. They both equal 5. You've got two distinct inputs, 1 and negative 1, giving you the same output. It's not a one-to-one function. However, if we restrict the domain, you might term an unnatural way. Well, no, this is still pretty natural. Then it becomes one-to-one, because then we're just talking about half the parabola here. We're talking about this half of the parabola. And that piece of the graph, ignoring the other part of the parabola, does pass the horizontal line test. All horizontal lines go through it at most once. So that's what we want to think about. And that informs how we find the inverse function as well. I need to take this equation and solve for x, subtract 4 from both sides. Then, do I take the positive square root or the negative square root? Since the x values for the original function were greater than or equal to 0, I want these x values to be greater than or equal to 0. So that means I take the positive square root. X equals positive square root of y minus 4. If, however, the domain of f had been restricted to be minus infinity to 0, then here I would actually take the negative square root, because the graph would be the piece over here and the x values would be negative. So another reason to emphasize that it's not necessarily always a good idea to swap the x and the y here. This would be f inverse of y, and that's fine for the answer. As far as a symbolic answer, again, it doesn't matter what the variable name is. If you want to do the swapping, you could write y equals f inverse of x is square root of x minus 4. And if you do that, that does have the benefit of having the reflection property like this. The graph of f inverse would be the reflection of this one. It would look about like that, somewhere about like that, which makes sense because it's a transformation of the square root function, thinking about parent functions again, to the right by 4 units. Okay? Actually, if you don't swap the x and the y, how do you graph such a thing? Well, there's 2 approaches. You could swap the labeling for the axes, call that the y-axis and this the x-axis. Or alternatively, you could say this original graph is still the graph of this function, except you're changing your perspective about what's the independent variable axis. You're thinking of the vertical axis as being the inputs and the horizontal axis as being the outputs. Yeah, if that was kind of fast and confusing, take the time to think about it. I think it's worthwhile. Part C. F of x is square root of x minus 3 plus 1. The domain is all x I could have added in the real number system such that the output is a real number, not a complex number. All right. So what are we doing here? Let's think about the graph. We thought about a problem similar to this before. Take the square root function, shift it to the right by 3 units, and then plus 1 means we shift it upward by 1 unit. The graph is going to look about like that. It is a one-to-one function. It's got an inverse function, which can be found by solving this equation for x. Subtract 1 from both sides. Then, to get rid of the square root, square both sides. And then add 3 to both sides. So x equals f inverse of y will be y minus 1 quantity squared plus 3, which can be simplified by expansion to y squared minus 2y. Negative 1 squared is 1, plus 3 is 4. That's fine for one formula. For the inverse function, you could also, again, swap the variables. Y equals f inverse of x would be x squared minus 2x plus 4. I'm realizing I forgot the domain and range for part B. Let's do that quick before we come back to the domain and range for part C. The range in part B for the original function was all y values greater than or equal to 4. For the inverse function, the domain and the range get swapped. So this becomes all x values greater than or equal to 4, and the range for this formula here is going to be the domain of the original. There's supposed to be an f inverse in there, so I'm going kind of quickly and making mistakes here. That'll be 0 to infinity. These get swapped for the inverse function. Coming back down here, the domain turns out to be, we should specify what it is, 3 to infinity. And the range of f is going to be, look, think about the outputs here, 1 to infinity. And those get swapped for the inverse function. Here for the inverse function, the domain will be 1 to infinity, and the range will be 3 to infinity. And as far as graphing it, it's going to be half of a parabola. You might prefer thinking about this form of it, except use an x instead of a y. Parabola opening upward, vertex at 1, 3. Let's see, so that'll be about like this, and it'll be the reflection across y equals x. I know I'm going kind of fast here. It'll look about like that. That'll be the graph of f inverse right there. Part D. Rational function, x plus 1 over x minus 2. The domain is all x where x is not equal to 2. That'll be minus infinity to 2, union with 2 to infinity. It's got a vertical asymptote at 2. As far as finding a formula, we solve for x in terms of y. You might look at that and say, how in the world am I going to do that? I've got an x in both the top and the bottom there. Just take a deep breath, multiply both sides by x minus 2 first, effectively cross multiplication, and simplify. We want to solve for x, so get all the x terms on the left, say, like this, and everything else on the right, like that. Factor out an x, and it looks like x equals f inverse of y would be 2y plus 1 over y minus 1. If you want to swap the y and the x, you'd write y equals f inverse of x equals 2x plus 1 over x minus 1. The domain and the range would get swapped. We haven't identified the range up here yet. It would be similar to graphing rational function we did before. Horizontal asymptote of this occurs at 1 over 1, which is 1. And that would mean the range, it turns out, will be every y value except 1. In interval notation, you'd write it this way. And this becomes the range of f inverse, while this becomes the domain of f inverse. Again, they swap. Let's try to draw quick graphs. For the original function, vertical asymptote at 2, horizontal asymptote at 1. I'm going very quickly here. You should take the time to think about this. X-intercept at -1. As x approaches 2 from the left, got positive numbers divided by negative numbers. It's going to look like this. Let's see. In the y-intercept is at -1/2. Going to look about like this. And over here, it's going to look about like this. It's pretty similar to that other example. For the graph, the inverse function, you got to flip it across the line y equals x. If we're thinking about the formula in the usual way, at least. Oh, it's kind of tricky, but let's see if we can do it here. X and y asymptotes are going to get swapped, actually. Let's see here. This gets tricky. Let's see. If you swing this across that red dashed line, oh boy, can I do this? This point is going to go to this point here, and this point will go to this point. Boy, I think it's going to look about like this. And over here, with looking at the black dashed lines, it's going to look about like that. Boy, that's confusing. That should be what the graph, the inverse function, looks like if I have not made a mistake. That's pretty confusing. You're going to want to take the time to go slowly through this problem again and think about it. 2 more problems and we'll be done. Number 7 is a word problem. Suppose 1,000 meters of fencing is available to partition a rectangular shaped field as shown below, like this. So all these black lines are the fence. Part A, express the total area of the field as a function of x. Part B, what value of x will maximize the total area? And part C, what is the actual maximum area? And we're not going to use calculus here. We're going to use just plain old algebra to think about this. The function is going to be quadratic. So first we have to express the total area of the field as a function of x. The area of a rectangle is x times y. But we want to get rid of the y. We want to write this just in terms of x. How do you do that? You can use the fact that you've got a limited amount of fencing. That's called a constraint. The total amount of fencing is 1,000. 4x for these 4 lines plus 2y for these 2 lines has to equal 1,000. The perimeter, including the ones in the middle, is 4x plus 2y. That's got to equal 1,000. I can solve that equation for y in terms of x and then plug it back into here to get a plain old function of x. 2y will be 1,000 minus 4x, and that means y will be 500 minus 2x. Substitute. You could write a equals f of x equals x times the entire expression 500 minus 2x. You can simplify that to 500x minus 2x squared, or if you prefer, minus 2x squared plus 500x. It's a quadratic with a 0 constant term. Well, this is the formula. That's part A. Okay, we express the total area as a function of x. Part B, again, what value of x will maximize the total area? Think about the graph of this. It's a quadratic function with a coefficient of x squared that's negative. It's going to be a parabola opening downward. The x-intercepts are easy, where these two things are 0. 0, which is also the y-intercept. And where is that 0? It's 0 when x is 250. 250. Graph's got to look like this. And in fact, as far as the application goes, we only care about what happens when x is between 0 and 250, because otherwise the output of this function is going to be negative, and that means it's not an allowed value of x. If x is too big, you're going to have over 1,000 meters of fencing. You have to satisfy this constraint still. So the domain for the application is just between 0 and 250. And the high point is where the vertex is. So what we need to do is we need to complete the square to help us find that vertex. Or realize it occurs halfway between the x-intercepts. You can do that too. That's the quicker way to do it. That will be the answer to part C. That'll be the value of x that maximizes the area. Value of x in meters that maximizes the area. Maximizes what I'm trying to write there. The area. What is the actual maximum area? It'd be the second coordinate at this point, the y value. I need to find f of 250. Probably easier to think about it in the factor form, actually. That'll be 250 times, I made a mistake, didn't I? 125. Made a mistake, 125. Yikes. F of 125. Probably easier in the factored form. 125 times 500 minus 2 times 125. 2 times 125 is 250. 500 minus 250 is 250. Going too fast here, I think. So I get 125 times 250. The maximum area is 31,250 square meters. That'll be the maximum area. You could just double check it here as well by plugging it into this form. X equals 125. 125 squared times -2 plus 500 times 125 also gives you 31,250. You can complete the square here to confirm the vertex form if you like. You'd want to factor out a -2 like this. That would be a minus 250 x there. You'd want to then take the coefficient of x, the -250, divided by 2 to get minus 125, and then square that number. Minus 125 squared is the same as positive 125 squared. 15,625. But then you need to compensate by the fact that we really added -2 times that. So compensate by adding positive 31,250. And this is a perfect square. You could write this as -2 times x minus 125 quantity squared plus 31,250. That would confirm that the vertex occurs at x equals 125 and y equals 31,250. That is the y coordinate here. So to summarize, the value of x where the maximum area occurs is 125 meters, and the maximum area itself is 31,250 square meters. And if you're trying to maximize area here, which is a natural thing to want to do for this field, that's what you would want to pick for x, 125 meters. And you could also find the corresponding value of y to be 250 meters. We are on to the last problem, yay! And it's a calculator required problem. Let f of x be this quartic function, fourth degree polynomial. 2x to the fourth minus 10x squared plus 4x minus 5. Part A, draw the graph of f in an appropriate viewing rectangle. Yeah, we'll want to use our calculator. Part B, is f 1 to 1, why or why not? Actually, you should be able to answer that really quickly based on the fact that this is an even degree polynomial. Part C, find the local maximum and minimum values of f and the values of x where they occur. We'll have to look at the graph and use graphing calculator features. D, find the approximate range of f. Yes, approximate, it won't be exact. E, find the approximate intervals on which f is increasing and decreasing. So we'll use our calculator right away. What should we pick for the window? That's hard to say, though we can use a little bit of guidance here. Let's just get the function in here first. 2x to the fourth minus 10x squared plus 4x minus 5. Oops, minus 5. First thing to realize is the y-intercept is going to be minus 5, right? F of 0 is going to be minus 5. And near 0, the terms of higher power are really, really small when x is close to 0. So what that means is the function acts like a straight line with a slope of 4 and a y-intercept of negative 5 near 0. It's got curvature to it, but the closer you get to 0, the more it looks like a straight line. That's an important fact from calculus, actually. A line with a slope of 4 and a y-intercept of negative 5. So you can start to imagine the graph. The fact that it's an even power of x means the graph, the end behavior is, and it's a positive coefficient, is going up as x goes to plus infinity or as x goes to minus infinity. There could be some wiggles in the graph, being a fourth degree. You know, these numbers, the negative 10 there is fairly far from 0. I don't think we're going to have to pick a very big window to see probably all the x-intercepts here. So let's try x going from negative 5 to 5. And how big should y be? Probably bigger, like maybe negative 50 to 50 or something. Let's just see what we see. And there we go. And yeah, that's giving us a pretty decent picture. That was a pretty good window to pick. Near 0, the y-intercept there is negative 5. It doesn't look like the slope is 4. It is a positive slope there. But it is, it's just because the scales and the axes are different. So that's essentially part A. Let me try to redraw what I had in the calculator here. It ends up looking about like this. Is about what it looked like right there, okay? Not a super great graph, but that's what it looked like. Is F 1-to-1? No. No, why not? Fails the horizontal line test. There are horizontal lines that go through more than once, meaning for many outputs there are more than one input. There are distinct inputs that can give you the same output, though it's hard to say exactly what those numbers are. Part C, find the local max and min values. Here's a local min point. Here's another local min point. These are like bottoms of valleys. And here's a local max point right about there. So we want to try to estimate those points using calculator features is the goal. So local min near there, let's go ahead and go to calculate menu, minimum. If we're near this point over here, left bound, right bound, and guess. So local min, could write local min value is the output. It's approximately the y value there, negative 24.01. We're after 2 decimal places here in the directions. At x is approximately negative 1.67. I'll go on to the next point. It's a maximum, a local maximum, left bound, say right around here, right bound, right around there, and guess right around there. Local max then is the y-coordinate there, negative 4.596 rounds to negative 4.60. That's a negative 4.60 at x is approximately 0.20. And the last one will be a minimum, left bound, right bound, and guess. That's a local min value of approximately negative 11.39 at x is approximately 1.47. Okay. Part D says find the approximate range. And so this was part C. Part D is the approximate range. What are all the possible y-coordinates? Go from the very most low point here, the global minimum, occurring, that's this value here, and go up forever and ever. The approximate range is about negative 24.01 to infinity. Now this is not exactly right because the exact answers here are going to be irrational numbers, but this is an approximate answer for the range of f. The domain is all real numbers. Part E, find the approximate intervals on which f is increasing and which f is decreasing. You need to focus on the x values where you change from decreasing to increasing, then back to decreasing again, then back to increasing. It's going to be increasing on between here and here and from here to the right. So this is approximate. Negative 1.67 to 0.2. Unioned with 1.47 to infinity. And it's going to be decreasing from minus infinity up to negative 1.67, and then also between these two numbers, between 0.2 and 1.47. Minus infinity up to negative 1.67, unioned with 0.20 to 1.47. And again, these are approximate answers, as are all the answers in this problem. Thanks for watching.